بسم الله الرحمن الرحيم والصلاة والسلام على الله المرسلين سيدنا محمد وعلى آله وصحبه وسلم. ما زلنا في سلسلة نظرية الأوتار مقارنة مع نظريات علي يوسف، وها هي الحلقة 12 والتي دخلنا فيها ما يسمى بالأغشية. وعنوان هذه الحلقة الاتفاقات بين نظرية علي يوسف ونظرية الأغشية. هناك اتفاقات كثيرة حقيقة في هذه الحلقة سنجدها، وأيضا ليس اتفاقات فقط، وإنما نظرية علي يوسف تفسر أشياء كثيرة في نظرية الأغشية، ابتداء من شرط ديليتشي وإلى الاكسايتيشنز وطرد الكتل وأنواع الحركة، وأيضا معادلة الحركة في الأغشية وكل ذلك في أنواع الكتل، وحتى أنه جميع الكتل عند جمع جميع الكتل المطرودة من الأغشية تعبر عن النسبية الخاصة، ولماذا تعبر عن النسبية الخاصة والفضاء المسطح. كل ذلك فسرته نظرية علي يوسف. وبالتالي يمكن أن نقول هنا أن نظرية علي يوسف يمكن أن تمهد لإجراء تجارب دقيقة لنظرية الأوتار. نحن نعلم أن نظرية الأوتار حتى الآن ليست لديها تجارب لأنها أبعاد صغيرة جدا، لكن باستخدام نظرية علي يوسف يمكن لهذه النظرية أن تجرب بأبعاد أكبر، ويمكن اختبارها، وبالتالي يمكن التأكد من صحتها ومن خطأها. وبالتالي نظرية علي يوسف تستطيع تقديم أشياء كثيرة لنظرية علي يوسف، يعني لا نظرية الأوتار. لاحظ هنا أن نظرية علي يوسف في السلسلة السابقة تحدثنا عن الأبعاد الكبيرة، والآن نتحدث عن أوتار، أبعاد صغيرة جدا عند أبعاد بلانك مربعا. طيب لاحظ هذا الأمر الغريب، إنه نظرية علي يوسف تفسر كل ذلك، وهذا يدل على ماذا؟ يدل على أن نظرية علي يوسف هي نظرية شاملة لكل الفضاء، شامل لكل الفيزياء. وهذا واضح لأنه في ميكانيك الكم إذا أردت أن تستخدم الفيزياء الكلاسيكية في الأكشن، فإنك تستطيع باستخدام ما يسمى بسيمي كلاسيكال. الغريب في نظرية الأوتار أيضا تستطيع أن تمثل الأكشن عن طريق الفيزياء الكلاسيكية. وهذا واضح ما دام أنت استخدمت الفيزياء الكلاسيكية في الأكشن في نظرية الأوتار وفي ميكانيك الكم طيب ما الذي يجعل الفيزياء الكلاسيكية تصف ميكانيك الكم؟ ما الذي يجعل يعني يرفض ذلك؟ فنظرية علي يوسف تخبرنا بأن الفيزياء الكلاسيكية تستطيع وصف العالم الكمي، فقط علينا أن نختبر أشياء، يعني مثلا نعتبر أن الكتلة غير ثابتة وتعتمد على المرجع الملاحظ، وأن القوى الكونية الأربع هي عبارة عن قوى يعني تعتمد على المسافة وليس ثابتة، وأن الفضاء أيضا هو غير ثابت يعتمد على المسافة أو الملاحظ. كل ذلك تجعل الفيزياء الكلاسيكية تصف ميكانيك الكم، وتصف الأوتار، وتصف الكون، وتصف أي شيء بكل أريحية. فهذا ما خرجت به بطول هذه السلاسل التي درستها والذي شرحتها في هذه الفيديوهات. الآن تعالوا نشوف مدى يعني حجم الاتفاقات بين نظرية علي يوسف ونظرية الأغشية بما يسمى بشرط ديليتشي. شرط ديليتشي الذي يعطينا الكائنات الأغشية، وأيضا تنطبق فيها نظرية علي يوسف. تعالوا نشوف.
Okay, so we discussed open strings. So let's go back to the open string. For the open string say after we fixed the worksheet to be flat, then worksheet action can be written as the following. Okay. So you can, when you obtain the equation motion for x, so you will then have something like this. So you need to do an integration by part. Plus a total derivative term, okay? Plus a total derivative term, and total derivative term, we induce a term on the boundary if you have an open string. Say at sigma equal to 0 and pi. Okay? So, so this is still d tau. And so from this term, you get equation motion. And then you induce a boundary term evaluated, because open string there's the two boundaries at 0 and pi. Then you induce such a boundary term at the boundary we need to also get rid of. Otherwise, the equation motion is not satisfied. And what we discussed is so-called Newman boundary conditions. It's just take the partial sigma equal to 0, partial sigma x mu to be 0. But in general, for any mu, say for any mu, you have a choice of 4 boundary conditions. You can choose delta x mu equal to 0, or partial sigma x mu equal to 0, say at sigma equal to 0. And you have the similar choices at sigma equal to pi. So altogether, you have actually 4 possible boundary conditions for each direction. So for each direction, you have 4 possible boundary conditions. If you consider all possible directions, there are many, many different boundary conditions. Okay? There are in principle many, many different boundary conditions. So let's now look at what the other boundary conditions mean. Okay? We look at the case which is you just impose this everywhere at both sigma equal to 0 and sigma equal to pi, and for all directions. But now let us explore these more general boundary conditions. First, let's just quickly look at what this boundary. So this is called the Dirichlet boundary condition. This is called the Newman. So first, let's look at what does this boundary condition mean. Okay. So if we have, say, let's consider some direction I. Say delta xi equal to 0. Say at sigma equal to 0. Say tau equal to 0. So this is the example of this, say, Dirichlet boundary condition in the I direction. So suppose at sigma equal to 0, you impose this. So what this means is that the variation of xi at sigma equal to 0 at all time does not change. So tau is like a parameterize your worksheet time, the worksheet motion. So this tells you that at all time, the value of the xi does not change at the end point. So what this means, this directly translates into xi sigma equal to 0 and tau should be a constant. Okay? Should be a constant. So this is the Dirichlet condition. And so let's look at some examples to understand a little bit more explicitly what this kind of condition, what this Dirichlet condition means. Okay. So let's first consider an example. say suppose in all directions, say from 0 to d minus 2, okay, we use, suppose, use Newman boundary condition as what we did before for both sigma equal to 0 and pi. But for the last coordinate, say let's d minus 1, okay, so let's impose the Dirichlet boundary condition. Say let's take it to be A at sigma, both sigma and 0 equal to pi. Okay, so for the moment, let's take the boundary condition to be same at both sigma equal to 0 and pi. So let's look at what this condition means. Okay, let's look at this example. So what this condition means, so let's draw a figure. So I cannot draw many directions. In particular, I cannot draw 26 dimensions. So let me call the horizontal axis is all the connection of all the dimensions up to d minus 2. And this axis is the d minus 1. Okay? Then the end point, the x d minus 1 equal to a at the end point. So suppose this is the line of x equal to a. Okay, so suppose this is the hypersurface for x d minus 1 equal to a. Then that boundary condition tells you that whatever open string, the motion, the end point must be restricted to this hypersurface. Okay? So that's what this geometrically what this condition means. It just says let's consider x d minus 1 equal to a, which is a hypersurface in space-time, and then this condition means that the end point of the string must be restricted to this surface. The interior of the string can be have low restriction, but end point have to be on this surface. Okay, is this clear? Okay, so you can generalize. So this is the first example. You can generalize. Let's consider x from 0 to some value p. Of course, p is smaller than the total number of dimensions, which is n for sigma 0 and the pi. And then the rest, say xp plus 1, xp plus 2, to xd minus 1, these directions, we impose the Dirichlet boundary conditions. And let me call this some vector A for both sigma and sigma equal to 0 and pi. Okay, so A is just some constant vector of the same dimension as the number of x here. Okay, the same as the number of x here, and this is just a more general way to impose this to more directions. Okay. Is this notation clear? Yes?
Wait, so why is there a repeated superscript?
Oh, sorry. P minus P plus 2. Yes?
Maybe, do we talk about like a different 0 and pi behaviors, or is that not interesting?
No, we will talk about that. Let's look at simple case first. Yeah. So is this notation clear? So again, I can do this on the similar plot like this. So now horizontal axis, I do x0 to p, and a vertical axis, I do p plus 1 all the way to d minus 1. So now both axes are multiple dimensional. And then this specifies, so this A specifies a p plus 1 dimensional hypersurface surface, right? So the value of those coordinates are fixed, but the value of those coordinates can be arbitrary. So there's p plus 1 free parameter here, okay? And so this is a p plus 1 dimensional surface in the space-time. And this condition means that the endpoint of the whatever open string must be restricted to this surface. Okay? Is the picture clear? Yes?
Sorry, I missed it.
Yeah, we are talking about how to impose what's the meaning of impose the Dirichlet boundary condition instead of Neumann boundary condition. So we now impose the Dirichlet boundary condition, which corresponding to the evaluation of the endpoint should be 0, and then this can be specified by the endpoint should take some constant value, and so that's the geometric way to think about this different Dirichlet boundary conditions. Okay. So if you look at this naively, so previously when we considered the Neumann boundary condition for all directions, then the string, then there's no restriction to the string, then the string can move anywhere. Okay. So now when in some directions we impose the Dirichlet condition, then we see that the motion of the string get restricted, and at this endpoint now have to lie some subdimension of the space-time. Okay. So at first sight, this seems to be a nonsensical thing to do. Then the string, then there's no restriction to the string, then the string can move anywhere. Okay. So now when in some directions we impose the Dirichlet condition, then we see that the motion of the string get restricted, and at this endpoint now have to lie some subdimension of the space-time. Okay. So at first sight, this seems to be a nonsensical thing to do. Just you say, you ask, why somehow I have to restrict some open strings to some submanifold in the space-time? Okay. So why should I do that? In particular, that breaks Lorentz symmetry. Okay, in particular, that breaks Lorentz. So the nice thing about the Neumann boundary condition we did before, in all directions, so that respects Lorentz symmetry. And once you introduce some directions to the Dirichlet boundary condition, you necessarily break Lorentz symmetry because you select out some directions versus some other. Okay, and
طبعا يعني للذين يعني لم يفهموا بداية هذه المحاضرة هي طبعا عندما تم اشتقاق معادلات الحركة لنظرية الأوتار. هناك كان شرطين، شرط يسمى شرط نيومان، والشرط الثاني يسمى شرط ديليتشي. شرط ديليتشي variation of x يساوي 0 عند سيجما يساوي 0 باي، وشرط نيومان هو بارشل جاما مضروبة في بارشل جاما مضروبة في اكس يساوي 0 أيضا عند 0 باي. و في يعني في المحاضرات الثلاثة السابقة كنا حلينا شرط نيومان ووجدنا الجرافيتون ووجدنا التاكيون ووجدنا. الآن نحن نحاول أن نحل شرط ديليتشي، وهو هذا الشرط الذي يعطينا الدي برين، يعطينا الأغشية. أغشية ثنائية البعد هذه أو متعددة الأبعاد. هذه الأغشية تتحرك فيها السترينج، يعني تكون هي ملتصقة بها وتتحرك فيها هي. وهذا ما ذكره الآن المحاضرة أنها لا تحترم شرط لورنز، تكسير لورنز، تكسير تناظر لورنز. طيب تعال نستمر.
And so you necessarily break Lorentz symmetry. You also break translation symmetry because you have to specify some submanifold. You also break the translation symmetry. So at first sight, this seems to be a nonsensical thing to do. So that's why for many years, actually, people did not look at this object, even though for a person to work out string theory on the first day, you should already realize the boundary conditions, okay? But for many years, people did not pay attention to these kind of boundary conditions. It turns out those boundary conditions plays a key role in string theory. And the key is to take a slight different perspective at those submanifolds, okay? So now, what you should think about is what you think about is the following. So you think about maybe for the whole space-time, only closed string is the most natural object. So it can move anywhere. But then there are some special places in the space-time, some kind of defect. And at those defects, the closed string can break to become open string. Okay? Can become open string. And if you take that perspective, then that gives special meaning to such kind of special submanifold which open string can end. Then there's some kind of object there. Because of the existence of certain object there, then the open string can end there. Okay? Yes?
So indeed, if you have that perspective, then instead of having it lie along hyperplanes, I mean, is it more natural to have it just lie upon some other manifold?
Oh, you can. Yeah, I'm just telling you the simplest example. Sure. And once you realize in this simple example, then you can generalize the arbitrarily complicated scenario you can imagine. Great. Yeah. Now let's just think about in the simplest case. Imposing those boundary conditions become natural if you think those places in space-time are special places which something can happen. It's not the same as other places, okay? And to say those places happen, so you give a name. So you imagine. So for example, you can imagine some space-time defect. So sitting at, say, this xp plus 1, x equal to a, okay, sitting at that location, so where open string can end. So such a defect, we call it debrain. We give a name. Okay.
طبعا أريد هنا أن أضيف معلومة ربما تكون مهمة جدا. بالنسبة لنظرية علي يوسف ستتعامل مع الدي برين كأجسام مهددة للفضاء ثنائي الأبعاد. وبالتالي سنتابع الاشتقاقات والمعادلات الرياضية والنتائج التي توصل عليها باعتبار أن الفضاء الثنائي الأبعاد سيدافع عن نفسه. طيب كيف ذلك؟ ذكر المحاضرة أن هذه الديب برينز يعني عند الديب برينز هذه تفتح كلوز سترينج وتصبح اوبن، تفتح وتصبح اوبن. نحن نعرف ان كلوز سترينج هي تخرج من الاشياء الثقيلة جدا الاثقل من الاوبن، وبالتالي هذه ايضا لديها خاصية في نظرية علي يوسف، حاليا لا استحضرها حقيقة، لكن هذه ايضا فيها تفسير لنظرية علي يوسف. لكن ما اريد ان اقوله ان الدي برين تعتبر كما ذكر المحاضر هي الديفكت في الفضاء رباعي الابعاد او الفضاء متعدد الابعاد، اللي هو من بي زائد 1 الى دي ناقص 1، هذا الفضاء الغريب، فهي تعتبر ديفكت، وبالتالي سيحاول ان يعتبرها الفضاء الثنائي الابعاد غير متناظر كتهديد له، وبالتالي مفترض ان تكون المعادلات كلها تخرج بهذه الآلية. الفضاء الثنائي الأبعاد يحاول الدفاع عن نفسه. طبعا موضوع غلق أو فتح السترينج عند الحدود في هذا يمكن نعتبره شيء آخر، وهو أن بما أن السترينج المغلق يفتح في عند السطح البرينز هذه، يمكن نعتبر العكس، أن السترينج المغلق ينبع من هنا، والسترينج المفتوح هو الذي يوصل مثلا من برين لبرين. سنرى هذا التوصيل، السترينج يربط بين برين وبرين، ويجب أن نجد له تفسير من نظرية علي يوسف ماذا يمثل. لكن يمكن نفترض أن الكلوز سترينج تنبع من الدي برين، وبالتالي تطرد موجات الجاذبية. الدي برين تطرد موجات الجاذبية. طيب ماذا عن السترينج المفتوح اللي هو الضوء؟ سنعرف ذلك، لأن الضوء مرتبط بهذا، لا إذا خرج بشكل موجات جاذبية، ولكنه في الحقيقة هو الضوء السترينج الأوبن سترينج لا يخرج، إنما يرتبط بين هذا وذاك، أو من سطح البرين هذا إلى أي سطح آخر، وهذا يجب أن يكون له تفسير في نظرية علي يوسف. أنا حقيقة لا أعلم حاليا، لكن فسرت الكلوز الذي يفتح في البرين يمكن أن يكون لديه نتيجة معاكسة، اللي هو يخرج من البرين وينغلق مباشرة، بالتالي تضرب موجات جاذبية. وموجات الجاذبية طبعا ذكرنا في الحلقة الفاتت أنها عند الطاقات المنخفضة لو انرجيز، هاي انرجيز تضرب ماسيف بارتكلز، هاي انرجيز لو تضرب جيج، والكلوز هي اينشتاين جرافيتي، وهي موجات الجاذبية. طيب تعالوا نواصل حتى نكتشف مزيدا من المفاجآت والكنوز من هذه الآليات. تذكر هذه الآلية التي شرحتها الآن، في جميع المعادلات التي تشتق يجب أن تحمل لنا أخبارا وتطابق هذه الآلية. طيب تعالوا نواصل.
Because it's a dirichlet boundary condition, and the brane because it's some extended surface, okay? And so we often use the notation, say, dp brane. So P denotes the number of spatial dimensions along the brane, okay? So in this case, there's a P spatial dimensions along the plane, along the brain, so we call it DP brain. Okay. So right now, DP brain is merely just a place which you impose a boundary conditions, which open strings can end. But we will soon see that actually a DP brain is a dynamic object, and it's actually a dynamic object, and it actually can move, can fluctuate, can jump around, etc. Okay. And so also from this perspective, our previous Newman.
طبعا دي برين يصبح ديناميكال، لابد أن يصبح ذلك، لابد أن يصبح ديناميكال. لماذا؟ لأنه هو في صراع مع الفضاء. أنا قلت أنه يسبب تهديدا للفضاء ثاني الأبعاد، ولابد أن يكون ديناميكال، لابد أن فلكشويش عشان يطرد كتل، ولابد أن يصغر ويكبر ويكمب وهكذا. كل هذا من أجل أن يضعف، يستطيع الفضاء ثاني الأبعاد أن يضعف هذا الديفكت الذي يصبح في هذا الفضاء. طيب تعالوا نواصل.
Boundary condition. If we have Newman in all direction, so if we have a Newman boundary condition in all directions, then in this case, the open string can end everywhere. And anywhere. From this new perspective, we call this a space filling brain. We call that there is actually a space filling brain. Okay. So the Dirichlet the Newman boundary condition we considered before should be considered as actually you fill the whole space-time with such a brain, and then the string can in principle move anywhere. So for example, in the bosonic string we talked about before, this group is corresponding to a D25 brain. A D25 brain because there's a 25 spatial dimensions. Okay. Such a brain when you impose the Newman boundary condition in all directions. Or if you are in the superstring, which the total number of space-time is 10, and then the spatial dimension is 9, then you have D9. Then these are the D9 brains. Any questions about this? Yes?
These boundary conditions, they're imposed at the quantum level, right? It's not just that the classical solution has to have its endpoints on this D brain, but it's the fluctuations around the classical solution that we consider.
Yeah, we will talk about that. Any other questions? Good. So let me make a note. You can in principle impose the Dirichlet boundary condition in any direction you like, except in the x0 direction. Okay, it's because x0 cannot be a constant. So x0 is the time. It's our real time in the Minkowski space. So the string moves in this Minkowski space-time, and this x0 is that time. And the time cannot stand still. Okay, and in order to have this, you need that location to stand still. and the time cannot stand still. So this cannot be a constant. So you cannot impose the Dirichlet boundary condition in the time direction. So the smallest in the Minkowski space-time, the smallest will be a D0 brane, which imposes the Dirichlet boundary condition in all spatial directions, except in time. In time, you always impose the Newman. Then the smallest situation would be called D0 brane, which is a point. And then the open string can end on this point. Okay? Yes?
So one question. So this idea about calling the Neumann boundary conditions to like 225 brane or T9 brane. So this is a little bit perplexing because it seems like not imposing Dirichlet boundary conditions. This implies that not imposing Dirichlet boundary conditions is equivalent to applying Neumann boundary conditions, which is not. They're not like. I mean, they're like mutually exclusive. It's not like. So I mean, I don't understand why it is that. So does this thing behave like a 24 brane? Like, does it have the same properties as like a 24 brane or something like that?
Sorry, which, you mean 25 brane?
So what I'm saying is that it seems that the Neumann boundary conditions have a different character than, like a different flavor of how they work than the Dirichlet boundary conditions. So it just seems strange to me that you would still call it a brane, like a D25 brane when you impose the Neumann.
No, so in those cases, for example, in this case, which we have Neumann boundary condition in all the other directions except one, then this is a 24-dimensional, then this is a 25-dimensional manifold which the string can end on. And I just...
Oh, I see. So right, you have to apply the Neumann boundary conditions to all of the other directions. Okay, I understand.
Yeah, so it's, Any other questions? Okay, good. So now let's consider more complicated, slightly more complicated boundary conditions. So by introducing this D brane, now you can have all different possible boundary conditions. As we said here, for each direction you can have, in principle, 4 possible choices. And then if you have 20, say, so for time direction you don't, but for 25 dimensions, 25 spatial dimensions, and each dimension you have 4 choices, then you have 4 to the power 25 possible choices of different boundary conditions. So now let's talk about the other boundary conditions. So, but use the picture of D brane, we can talk about them all. So let's consider more than one branes. Okay. So let's consider the situation. We have 2 such DP brane. So this direction is still x1, x0, 1 to p, and then this is all the transverse, all the other directions. So suppose you have a brane at A, and another brane at B. Okay, at the vector specified by B. Okay. So now in this case, we can have 4 types of open strings. We can have 4 types of open strings. For example, I can have an open string which ends on B. I can have an open string end on A. But I can also have an open string which go from B to A, and for open string from A to B. Okay. So in this case, the boundary condition would be the x01 to P is still a Newman boundary condition for both sigma equal to 0 and sigma equal to pi. But for the other directions, okay, you can have either your sigma 0 can either be in A or B, or sigma equal to pi can either be A or B. Okay, so that gives you the 4 types of strings. Okay, that gives you 4 types of different strings. Now you can also consider branes of different dimensions. So now you can consider branes of different dimensions.
طبعا هنا في معلومة مهمة أنه السترينج الذي يبدأ في البرين وينتهي بنفس البرين تتحكم فيه نيومان كونديشنز اللي هو الترافيق المعادلات اللي فاتت التي اشتغلناها وحليناها. أما السترينج الذي تربط بين 2 برين دي تعتبر لها خواصها. لماذا؟ لأنه تربط من برين لديه أبعاد أعلى إلى برين لديه أبعاد أقل، وبرين لديه أبعاد أعلى يعني كتلة أعلى، وبرين لديه أبعاد أقل يعني كتلة أقل. تعالوا نفهم هذا الأمر بهذه الآلية حتى نعرف نستكشف المعادلات كيف تكون.
Say, for example, suppose let's single out the 2 directions, d minus 2 and d minus 1. And let's suppose all the other directions are in the Newman direction. So let's consider 2 kinds of branes. One is that extended in the d minus 2 direction, say at some value of d minus 1. And let's consider another brane which is localized in both d minus 1 and d minus 2. Okay? Then you can again have 4 types of strings ending on itself, and then ending between these 2. So again, you can see the oriented string because we consider oriented string. So you can again consider a string like that. So let me call this brane 1, this brane 2. So let's consider the 1, 2 string. It's from 1 to 2. Then the 1, 2 string would corresponding to the boundary condition, say at d minus 2, say at sigma equal to 0, you impose the Newman boundary condition, okay, because it can move freely in the d minus 2 direction, and but in the at sigma equal to pi, then this should be fixed at some value. So let's suppose say this is A1, B1. Then at that we'll fixed at A1. Okay, so this is 1, 2 string. Then you can have one end which is a Newman boundary condition, but the other end which is the Dirichlet boundary condition. Okay, is this clear to you? And then for this 2, 1 string, then will be opposite. For the 2, 1 string, for the d minus 2 direction, at sigma equal to 0 will be the Dirichlet condition, but at sigma equal to pi would be the Newman condition. Okay, any questions about this? So these are pretty simple. You just need to get used to it and spend a couple minutes, draw a couple of diagrams, then you will be an expert. You will be an expert. This is pretty elementary. So important remark. So a DP brain as we said before, it breaks translation symmetry.
طبعا أي object break translation symmetry هذا يعني يشكل تهديدا للفضاء الثنائي الأبعاد غير المتناظر، لأن الفضاء الثنائي الأبعاد غير المتناظر هو يريد أن يجعل الفضاء أو الأشياء التي حوله أو التي عليه يجعلها مسطحة، كما رأينا في السلسلة السابقة النسبية العامة وعلم الكونيات. نجد أن الطاقة المظلمة ما هي إلا مقاومة الفضاء الثنائي الأبعاد والكتلة لزيادة في الكتلة، وبالتالي هو يحاول يجعل الفضاء مسطح، وبالتالي الفضاء غير مسطح هو يعمل بريك للورنز سيمتري، وبالتالي سيحاربه الفضاء الثنائي الأبعاد غير متناظر.
Translational and Lorentz symmetries. Okay. Of the original Minkowski spacetime to a subgroup. Say the subgroup is that you still have translation symmetry and the Lorentz symmetry along the brane direction. Say along the brane direction, you still can translate, your string can still translate in that direction. And still there's Lorentz symmetry in that direction. So there's still Poincare symmetry in 1p, 1 comma p, say in the time and the p spatial dimensions along the brane. And then you have rotational symmetries in the direction transverse to the brane. So that's d minus 1 minus p. Okay, so that's the rotation among those coordinates. So you can have the Lorentz symmetry along those directions, then the rotational symmetries along those directions. Okay, so this is for TP brane. So this is the remaining symmetry. So this is remaining.
طبعا الروتيشن مع زيادة الأبعاد، يعني هنا في تريك عجيب جدا يتفق مع نظرية يوسف. في حالة إن الأبعاد الأقل هي ترانسليشن سيمتري اللي هو بونكاري 1 بي 1 كوما بي ترانسليشن، أو أما عند زيادة الأبعاد اس او تعطينا سيمتري اس او دي ناقص 1 ناقص بي، وبالتالي هذا يتفق مع نظرية يوسف بأن زيادة الأبعاد فإن الفضاء الثنائي الأبعاد يفعل آليات إضافية عند زيادة الأبعاد، لأنه زيادة الأبعاد تكافئ زيادة الكتلة، فبالتالي فإن الفضاء الثنائي الأبعاد يفعل آليات إضافية، منها الروتيشن. طبعا من آليات الفضاء الثنائي الأبعاد غير المتناظر هو الروتيشن، وهذا أيضا يمكن نقول أنه النسق يتفق مع نظرية يوسف، وبالتالي اس او تكون في الأبعاد العليا دائما، و بونكاري 1 كوما بي 1 طبعا تايم وبي هي السبيس تكون في الأبعاد أقل. طيب تعالوا نواصل.
Symmetry. Say if you have a DP brane in the space-time. Of course, if you have multiple DP brane, etc., then it's broken even more. Yes.
Why do we assume that branes are topologically open, not compact?
Oh, yeah, we can talk. Yeah, here I'm just talking about the simplest situation. I'm imposing the simplest boundary condition, just like this kind of boundary conditions. And then this kind of boundary conditions applies to the infinite. Yeah, you can, once later we talk about the d-brane can be dynamical, etc. Then you can consider complicated configurations. Yes.
So far we consider one Newman boundary condition when derivative is 0, and then derivative when the x is fixed.
Yeah.
So how about condition when derivative is non-zero, and then so when d sigma x is non-zero, some constant number, and I remember there was like x plus derivative is equal to some constant.
You are saying something like this. You're saying the some combination of this.
Oh, the x plus derivative is.
Yeah. That can happen. That does not happen in the straight Minkowski space, because in the straight Minkowski space, this is the action. So you can only have one or the other. But if you say have Minkowski, but you turn on some electric field, then you can actually have such kind of mixed boundary conditions. Yeah, just there exist such stage. It depends on the specific dynamical situation. So this is empty, flat Minkowski space. Then you can only have those boundary conditions.
And when the derivative is equal to some constant, it also can be reduced to this bare phenomenon.
Sorry.
When d sigma x is equal to some non-zero constant.
That I'm not sure. That is different. Yeah, because that does not satisfy that boundary condition. So we have to look at the specific situation. Just for the flat Minkowski space, these are the only boundary conditions you can have. And we will not be able to do it in this course, but you can consider the situation because in open string you can have electromagnetic field, you can have a photon, so you can in principle turn on an electromagnetic field, and then that will modify the boundary condition. Then you can have actually mixed boundary conditions.
Do people ever consider this string between two d-branes as a topological defect? Because it's happening between.
You mean string between different d-branes?
Yes.
You consider the d-brane themselves as topological defect rather than the string between them as topological defect. The d-brane themselves are defect. Strings are just, yeah, as we will talk about it now. The strings on the d-brane, they're just the excitations of the d-branes. So now, after talking about those boundary conditions, then we can again go through the procedure of quantizing open string with those boundary conditions. Okay, then we see what do we get. Now let's talk about the open string spectrum on the DP brane. So yeah, as you can see already from those pictures, because they are restriction on their endpoints, so essentially those strings, they can only move along the direction of the brane. Okay, they can only move the direction along the brane. So essentially, they can be considered as living on the brane. Okay, so those open strings are living on those DP branes. Okay, so when we quantize those open strings, then we will get the excitations of those open strings, the state of those open strings, then on the D branes. Okay. So let me first introduce some notations. Previously, we have the notation mu refers to all directions. So now I separate into alpha and A, and the alpha is the Newman directions from 0 to P, and the A are the Dirichlet directions from P plus 1 to D minus 1. Okay, so there's D minus 1 minus P of them. Okay, so D minus 1 minus P of them. So for the Newman boundary conditions, just identical to what we had before. So let me just write it down to remind you. Okay, so these are the most general solution. So in this case.
طبعا علينا نركز أن السترينج هي excitations on deep brain. يعني السترينج تعتبر higher energies في الديب برين، والهاي انرجيز معروف انه يتم طرد فيها طرد الكتل وطرد الاشعاع وطرد لانه الفايبريشن اوف السترينج يعطينا الكتل، فبالتالي يتم طرد الكتل. يعني السترينج في على سطح البرين يعبر عن كتل خارجة من هذا البرين، وهذا يتفق مع نظرية على يوسف. طبعا هنا المعادلة هذه التي يكتبها هي معادلة نيومان المختصة ب الهاير انرجي والزيرو بوينت انرجي. حتى الزيرو بوينت انرجي موجودة هنا في هذه المعادلة، اللي هو كان جبناها من المعادلتين التي لم نستطع، يعني لم طبقنا في جيج فيكسين أعطتنا معادلتين. هذه المعادلتين أعطتنا الموشن اون ذا الورشيت، اللي هي على سطح السترينج، على سطح السترينج ذات نفسه او الفضاء القريب جدا من السترينج. بالاضافه الى معادله نيومان هي معادله اللورنز سيمتري ريسبكت، معادلات التي هي الاولى اكس الفا زائد 2 الفا برايم بي الفا تاو. دي هذه معادلة نيومان تعبر عن حركة السترينج ذات نفسه، حركة السنتر بتاع السترينج، السنتر ماس بتاع السترينج. بالإضافة للمعادلات الأخرى التي تمثل الاكسايتيشنز، هي حركة موجات على سطح السترينج، وحركة الموجات على سطح السترينج تعطينا الكتل. فنركز على هذا ونربطها بما نظرية على يوسف أن الفضاء ثنائي الأبعاد يتم طرد الكتل. طيب تعال نواصل.
In particular, if you remember, you have XL equal to XR. So the left moving and right moving are the same, controlled by the same function. And so that's why you get this cosine. And when you take the derivative of sigma becomes sine, then vanishes at the end point. Okay? So this story is just exactly identical as before. So now let's look at the Dirichlet conditions. So for the Dirichlet conditions, let's again write down the most general possible boundary conditions for Dirichlet boundary. First write down the most general solution for such a field. So you have XA, then 2I PA tau. Then you have R, tau minus sigma, and LA, tau plus sigma. Okay? But now the boundary condition we need to impose is XA and sigma equal to 0 and pi, sigma 0 tau and sigma pi tau equal to BA. So here I call them A, but let me call them B, because it's awkward to write A to the index A. So let me just call them B, the vector B. Okay? So now we have to impose this boundary condition. So you can immediately see that because of this boundary condition, XA have to be BA. Okay, XA have to be BA. And this PA have to be 0. PA have to be 0, otherwise you won't satisfy this condition because this changes with time. And then you want the sum of them to be 0 at x equal to 0, sigma equal to 0. So that gives you XL equal to minus XR. So this is from the boundary condition at sigma equal to 0. Okay? And then the boundary condition at sigma equal to pi you deduce both of them are periodic boundary conditions. They are periodic functions in 2 pi. Okay? They're periodic in 2 pi. You can see it easily. So at the tau sigma equal to 0, you just have xr tau plus xl tau equal to 0. Yeah, it should be equal to 0, so you should xl equal to minus xr. So now you can just write down explicitly, just still this is a periodic function in 2 pi, so the expansion is essentially the same. So the only difference for those directions is that now you have B alpha, BA. Now you don't have this term because this term is 0, and then A not equal to 0, alpha NA divided by N minus I N tau sine N sigma. Okay, there's some prefactor here I forgot to write, okay? Some alpha prime, etc. By convention, let's not worry about those things. Okay? So now you do quantization. So the quantization in Newman boundary condition, of course, identical to before. Oh, yeah, first let me just explain the PA equal to 0. Just make one remark. So this is, of course, expected. Because if the string is limited to moving on this plane, then of course it cannot move in the perpendicular direction. So cannot have center of mass momentum in the perpendicular direction. So this is indeed what you intuitively expect. Okay, the center of mass momentum can only be in the one direction, or can only be in the Newman directions. So the quantization of the Newman boundary condition of course is exactly the same as before, and actually quantization in Dirichlet directions with this setup also the same, also exactly the same. Because essentially the only change is the cosine sigma go to sine sigma. You can walk through that procedure, and you find that nothing really changes. It's also exactly the same as that of n. Okay. In particular, the commutation relations between all those modes does not change at all. Just are exactly the same as what you would have in the Newman case. So this is also physically lateral. This is also physically lateral. So imposing such boundary conditions, essentially you only restrict to the center of mass motion, so you can no longer move in the perpendicular directions. But the string can oscillate. But string can still oscillate in all 10 dimensions. There's no difference in the way the string oscillates. And so string still oscillates in 10 dimensions. So everything is the same. A string still oscillates in all directions. In particular, the 0-point energy is the same. 0-point energy on the worldsheet is the same. Okay. So this means that the mass formula we derived before for the Newman boundary condition will exactly apply without any change. Okay, without any change. In particular, the massless spectrum will also be essentially the massless or massive spectrum will be also be essentially exactly the same as before. 1 second.
طبعا هذا شيء طبيعي ومتوقع انه الاوسيليشن لا يتاثر، لكن الموشن perpendicular موشن التي تعبر عن الحركة في خط مستقيم أو في خط عمودي للديبرين هي التي تتأثر، لكن الأوسيليشنز لا تتأثر لأنها يتم فيها طرد الكتل، حسب نظرية يوسف، لهذا لا تتأثر، وبالتالي طاقة الفراغ لا تتأثر، وبالتالي excitation energy الهاير energy لا تتأثر، وكما ذكر أن السترينج تعتبر higher energies excitations بالنسبة للديبرين، وهذا أمر مهم جدا.
So let me just mention one point, that this is identical. Okay, that this is identical is actually related to that for the dirichlet boundary condition on both sides. This is still a periodic boundary, a periodic function 2 pi, and so you get this. In such a case, say if one endpoint is the Newman boundary condition, but the other endpoint is the Dirichlet boundary condition, then the story is a little bit more subtle, okay? And then you actually get to the frequency of each mode become half integer rather than integer, and then you will get the different 0-point energy, and there the spectrum will change, etc. Okay? So I will not do it now. Maybe I will put it in your next piece set so that you can do it yourself. Yeah, you have a question?
I think you answered it. The question was what happens if p equals 0? How can you utilize the light cone gauge contribution?
Oh, yeah, for the p equal to 0, yeah, indeed it's a little bit tricky to do the light cone gauge, yeah. Yeah, for p equal to 0, it's tricky to do light cone gauge, but you can do, using other quantization procedure, then you can do the same thing. Yeah, but the conclusion does not change between different p's. Yes?
Maybe I missed this, but for the two different brains, if you have a string going from one brain to another,
yeah.
You said from a point to a brain, the story changes. What about like from one brain to another? Is it exactly the same as this, or is it?
Oh yeah, that's also a good question, which I might already have something like this in the current p set. And if not, certainly I will put in the next p set because you asked. Yeah, you see there's a distance between them. So now you actually need to include the sigma term. Now you actually need to include the sigma term here and to account this difference. Because now the 0 and the pi is no longer the same. Yeah, here I don't need to put in the sigma term because the 0 and the pi are the same. Yeah.
So the 0-point energy would change? Yeah,
0-point energy will change. And essentially it's given by the mass of the string stretched between them. Mm-hmm. Yeah, so that will be that's a very instructive exercise. Actually, maybe I already put in the current piece, I don't remember. Anyway, other questions? Good.
The following content is provided under a Creative Commons license. The following
particular, the 0-point energy is the same. 0-point energy on the worksheet is the same, okay? So this means that the mass formula we derived before for the Newman boundary condition will exactly apply without any change, okay, without any change. In particular, the massless spectrum will also be essentially the massless or massive spectrum will be also be essentially the same as before. 1 second.
طبعا هذه هي الزيرو بوينت انرجي على الورك شيت، لكن إذا كانت السترينج تربط بين تو برين الوضع سيختلف.
So let me just mention one point, that this is identical, okay, that this is identical is actually related to that for the
أيضا هناك شيء آخر at higher energies excitation energies لابد أن الزيرو بوينت أن تختلف أيضا حسب ما ذكر في الحلقة السابقة من أجل أن تحقق الكونديشنز المعادلتين الإضافيتين.
To reach the boundary condition on both sides, this is still a periodic boundary, a periodic function 2 pi, and so you get this. In such a case, say if one endpoint is the Newman boundary condition, but the other endpoint is the Dirichlet boundary condition, then the story is a little bit more subtle, okay? And then you actually get to the frequency of each mode become half integer rather than integer, and then you will get the different 0-point energy, and there the spectrum will change, etc. Okay? So I will not do it now. Maybe I will put it in your next set so that you can do it yourself. Yeah, you have a question?
I think you answered it. The question was what happens if p equals 0? How can you utilize the light cone gauge configuration?
Oh, yeah, for the p equal to 0, yeah, indeed it's a little bit tricky to do the light cone gauge, yeah. Yeah, for p equal to 0, it's tricky to do light cone gauge, but you can do, using other quantization procedure, then you can do the same thing. Yeah, but the conclusion does not change between different p's. Yes?
Maybe I missed this, but for the two different brains, if you have a string going from one brain to another, is it from a point to a brain, the story changes? What about like from one brain to another? Is it exactly the same as this, or is it?
Oh, yeah, that's also a good question, which I might already have something like this in the current p set. And if not, certainly I will put in the next p set, because you asked. Yeah, you see there's a distance between them. So now you actually need to include the sigma term. Now you actually need to include the sigma term here, and to count this difference. Because now the 0 and the pi is no longer the same. Yeah, here I don't need to put in the sigma term because the 0 and the pi are the same. Yeah.
So the 0-point energy would change?
Yeah, 0-point energy will change. And essentially it's given by the mass of the string stretched between them. Mm-hmm. Yeah, so that will be that's a very instructive exercise. Actually, maybe I already put in the current piece, I don't remember.
هذا ما ذكرته أن الزيرو بوينت ستتغير نتيجة تغير الفضاء. هذا فضاء أعلى في البرين الأعلى في فضاء أعلى أبعاده أعلى والفضاء الآخر فضاء أقل لابد أن الزيرو بوينت تتغير حسب نظرية على يوسف وهذا صحيح تماما تتفق معي.
Anyway, other questions? Good. So now let's look at more explicitly at the open string spectrum. So again, it's the same thing, you just act alpha minus n1, mu1. You can act m1 times, say nk, mu k, nk, mk. The only difference is now your vacuum state can only have momentum in the p alpha direction. That's essentially the only difference. Okay? And again, the mass square, now is just minus p alpha, okay, only along the Newman directions. So this is really, then each mode on the string, each oscillation mode of the string now should really correspond to a particle or field in p plus 1 dimensional word volume of the DP brane. Okay, so we call this is the word volume. We call the directions. All these directions together is the word volume of the DP brane. So since that since the string can only move along the DP brane, so they can only corresponding to the field or particles within the DP brane. They cannot move in the opposite direction. They cannot move in the perpendicular direction. Okay, so they really live on the brane. Okay, and in this, then all those things may be considered as the excitations of the brains. Okay.
The string can be regarded as the excitation.
Yeah, that's right. Yeah, because you can excite certain strings and not excite strings, etc. And they're all moving along the brain. Yeah. And the important thing is that the states should fall into representations now of this symmetry, because that's the only remaining symmetry. Okay. This Poincare 1p and the rotation in the transverse directions. Okay. And again, just by this, you can show that you actually make sense only in the 26th dimension. Okay? Again, makes sense only in the 26th dimension. So now let's again look at the massless states. So as I mentioned before, the mass formula is exactly the same as before because the oscillation mode behaves exactly the same. So the mass formula exactly behaves the same as before. So the massless state then is the following. Yeah.
That when we see the particles in p+1 dimension word volume.
Yeah.
But you know that in quantum field theory, the particles is like a very local object. But the open string can, you know, one end of the open string located at one point, but not the other one located very far away. But is that picture same as the particle?
No. That's a good question. So when I say particles, I'm talking about the center of mass motion. Okay. Yeah, just for each oscillation modes, you see that's corresponding to for particular oscillation modes, then other than those quantum numbers. Let me finish this. I will answer that question. I will write this down. Then you see explicitly. So let's talk about massless states. So again, using the light cone. So again, we'll use the light cone. You can separate the direction into plus minus, and I in the Newman direction, and in the Dirichlet direction, again it's just the p+1 to d-1. Okay. And then the massless modes would be the same as before. You have alpha minus 1 I acting on p alpha, and the alpha minus 1 A acting on p alpha. And the plus infinite number plus the plus infinite number of massive modes. Okay. So let me just illustrate this point. So the light cone symmetry, as before, the light cone gauge further breaks this Poincare symmetry to only a subgroup. But you can already see from here, this must correspond to a vector particle. Okay, so this is like a massless vector. Massless vector. So to answer your question, so example, for for typical modes like this, the only quantum number you have is P alpha and this vector indices, this vector index. So from the perspective of the quantum number, and this really is just like a vector particle. Just like a vector particle. And then you can describe it by a vector field, etc. It is a very good question. Say, suppose in the situation in which I have a string, suppose the string is really very long, it's very big, then I should be able to see this one-dimensional structure. Indeed, then that means that even though this is just corresponding to one particular mode of the string. And to see the string structure, you have to be able to see, you can excite this into other different modes, etc.
Let's say if we just stretch the string.
Yeah.
I mean,
stretch the string corresponding to excite the string in a different way. It means leaving this particular state.
Oh, I see.
Just I'm talking about the interpretation of this particular state, which is like a space-time particle. Okay.
Actually, this state conversely decided all the configuration of the open string.
It determines all the configuration. It determines all the oscillation modes of the open string. Just the other oscillation modes, they are all not excited. Okay. But of course, if you can observe this one-dimensional object, then you can find ways to excite them, and then you know this is not a particle; it's a one-dimensional object, etc. But in order to see this one-dimensional structure, you have to probe a finer structure than just those quantum numbers. If those are the only quantum number you can probe, then it's like a particle.
طبعا هنا في موضوع في غاية الأهمية هو الاسترتش. يعني إذا كلما طال أصبح طويلا السترينج، هذا يعني more excitations. كلما استطال السترينج يحصل له استرتش، هذا يعني more excitations. سنراه بعد قليل عندما يكون من البرين تو برين، برين الهاير تو برين اللور. ماذا يعني هذا الاسترتش؟ لكننا الآن الحركة الآن على سطح وعلى نيومان دايركشن، وليس ديليتشي دايركشنز ونيومان دايركشنز، هو على سطح أو داخل الديبرين. هذه الاكسايتيشنز التي تحصل، وكلما زاد الستريتش زاد الطول السترينج، زادت الاكسايتيشنز، وكلما زادت أيضا ربما يكون كلما زادت الحركة، لأن هي على ما يسمى بي ألفا، يعني كمية التحرك في ألفا، يقصد النيومان دايركشنز. وكلما زادت البي ألفا كلما زاد الاكسايتيشنز. يعني هناك نوعين من الاكسايتيشنز، كلما طالت زاد الطول السترينج، وكلما زادت حركتي. طيب تعال نواصل.
So this is like a massless vector, but now those guys, they have an index A, which is not in the. They have an index A, which is not in the Poincare here. So those are now scalar fields. Okay, those are scalar fields on the world volume of the deep brains. Okay, so now we find so previously when we consider all Newman directions, we only see a vector field, say moving in all 26 dimensions. But now, so these massless modes, they give rise to a vector field, the massless vector field, A alpha, and d minus p minus 1 scalar field phi a. Okay? So essentially, when you introduce d-brane compared to the space-filling brane case, which we considered before, in the Newman direction, just some component of those gauge fields now become the oscillation in the transverse direction, and now they just essentially become a scalar field. Okay, is this clear? So now instead you have a smaller vector field plus some plus a bunch of scalar fields.
طبعا الماثلس فيلد، الماثلس بارتكلز على طول نيومان دايركشنز، والسكيلر فيلد على على الدايركشن العمودي، على الدايركشن العمودي. لهذا يكون ماسيف، لهذا يكون ماسيف، يعني بارتكلز تكون ماسيف اللي هي ميو وفاي، اللي هي تكون في الدايركشن دي ناقص ناقص 1 ناقص بي. وهذا أيضا يتفق مع نظرية، لأنه زيادة الابعاد يعني زيادة الكتلة، وبالتالي الجسيمات التي تخرج لابد أن تكون أكبر من الماثلس، بالإضافة للماثلس طبعا أكبر من الماثلس، لأنه الفضاء ثنائي الابعاد عند زيادة الكتلة يفعل آليته للدفاع عن نفسه ويطرد الكتل. يعني هناك في الماثلس كان راديشن، وفي الماسيف كتل وروتيشن أيضا، وهذه من آليات الفضاء الثنائي الابعاد للدفاع عن نفسه. طيب تعالوا نواصل.
As we said before, then the low energy effective action for such massless modes must have the structure, say, so this is in the p plus 1 dimensional volume of the string, say, of a Maxwell theory. And just as a, say, massless scalar field. And then, of course, there are more complicated contributions. Just this is a low energy. At low energy, then the structure of those excitations that must be described by this kind of low energy effective theory. Okay. Yeah, this is again just determined by the universality of a massless mode. So now there's a very. So now let me first note. Let me emphasize this, a point. Is that the number of massless modes, massless scalar fields. So we have such a bunch of scalar fields, okay? It's exactly the number of transverse directions. To the D brane. Okay? So essentially associated with each transverse direction you have a scalar excitations. You have a massless scalar field. Okay? And let me emphasize this point. So those scalar fields, some of you may can already have guessed, they have a very simple physical explanation. They have a very simple physical interpretation. And those scalar fields, they can be considered as describing the motions and the fluctuations of the D brane in the transverse directions. Okay? So for each transverse direction, you have such a massive scalar field. And each of scalar fields So more precisely, so more explicitly, just as a cartoon picture, suppose let's consider, say, the p minus 1 direction, p plus 1 direction, this direction, p plus 1 direction. So suppose you have a d brane sitting here at some value of a. Okay. So when we impose the Dirichlet boundary condition, yeah. So those are the x1, 0, 1, and p directions. Okay. Yeah. This is the x0 and p directions. You have a d brane sitting here at some value of a. So when we impose the Dirichlet boundary conditions, that boundary condition does not depend on the value of x0 and p, so they are same everywhere. So that's why I draw it flat, exact flat. But now if you have some excitations in the phi p plus 1 direction, so phi p plus 1 is a field in the world volume of the can have p alpha momentum. You can go to coordinate space, then there are functions just x1, xp, okay? x1, xp. And then the profile of this phi essentially tells you that the d brane, say if you have a scalar field excitation like this, then the shape of the d brane actually is no longer strictly flat, actually have a profile given by this scalar field. Okay? So I will not justify this precise, so this can be justified mathematically to really show that this is the case. Okay? And I will not do that here, but let me just mention some support for this picture. So okay. So first you can show at the worldsheet level having such excitations. Okay. So having such excitations, so which I just call it phi A excitations. So this is a picture in momentum space. Phi excitations modifies the Dirichlet boundary condition. Okay, so this you can show explicitly. So this is first point, which I will not go into there. And the second point is that you can actually work out the precise prefactor. There is a way, say by doing a string theory calculation, say by computing the partition function, etc. There's a way you can actually work out the prefactor, precise prefactor. So let me call this the equation star. So you can actually work out so that was just by general, this is just by general principle. Say if you have a massive spectrum, then the Lorentz must behave like this. And but this prefactor is not fixed, okay? And but you can actually with the interpretation phi, say as the fluctuations of this Dirichlet boundary condition, you can actually fix the precise prefactor here. So working out the precise. Okay. You can show that actually this action can be written as the following. Tp again is integrated only over the world volume of d branes p plus 1. And you actually, first we find actually there's a constant term when you work out the action precisely. And then you have this F term. And under this, and let me, actually I should have done it there. So there is a summation A over here, right? So this TP, this prefactor, is actually you can work out the prefactor.
طبعا هذا ما يأكد أيضا كلامي أنه السكيلر فيلد فاي هو الذي يحدد البريفاكتور اللي هو ثابت التناسب الذي سمي الآن BTB. يحدد لماذا؟ لأن الفاي عبارة عن اكسايتيشن تطرد كتل، فثابت التناسب غير محدد، لكن عندما يكون هناك الفاي موجود اكسايتيشنز هذه الفاي تعمل تحديد لأنه عبارة عن طرد كتل، طرد جسيمات. طرد الجسيمات يعمل ماذا؟ يجعل يقلل الاكسايتيشنز، وبالتالي تقليل الاكسايتيشنز تعمل على تثبيت طبعا الاكسايتيشن تتناسب مع انحناء الفضاء، وبالتالي تقليل الاكسايتيشنز على تقليل انحناء الفضاء، وهذا ما يجعل الفضاء مسطحا، وهذا أيضا نتفق مع نظريتي.
And this prefactor is given by the mass of a dp brane per unit volume, or in other words, the brane tension. So I will explain where does this come from, how do we define a brane tension, but for now let me just introduce this concept of brane tension. So if you work out the prefactor, you find the prefactor is precisely the brane tension, okay? Brane tension. So now if you look at this equation, so then this one is just like a static mass term. Okay, this one is like a static mass term. So you also find this one in this Lorentz effective action. But this one is very important because of the so this one is like static term. And now if you look at this term, so now if you consider the situation which A alpha is equal to 0, so you don't have any excitation of the vector field, but phi A only depend on t, only depend on the time. And then this effective action then will become.
طبعا هذا أيضا نتفق مع نظريتي. أنا ذكرت في الفيديو اللي فات أنه فاي ربما يكون عبارة عن التايم دايليشن. الآن هو ذكر أنه يعتمد على التايم، إذن هو فعلا يعتبر التايم دايليشن. هذا شيء غريب جدا.
TP, then the volume of the P, then dt 1/2 phi dot A square. Okay? And so Vp is the volume of dp brane. Volume of the dp brane. And this tension times dp brane, so this is just the mass. So this is just the mass. So so you can rewrite this just 1/2 and d brane phi dot square. Okay. And then d brane.
الله أكبر.
So the TP times the